Hi everyone, my name is Minghao and I'm a research assistant at the Harmony Center. I will introduce AC analysis of carbon-based elastomeric composites for printed sensors and electronics. I will introduce this project following this order: the background and aim, the characterization method and the results, and then discussion and conclusion. Microelectronics and sensors based on traditional rigid materials and technologies result to devices that cannot conform to non-flat surface and can damage soft materials or tissues, particularly when under mechanical motion and stress. Compared with traditional rigid electronic devices, flexible and stretchable electronic devices can tolerate greater deformation, so that they can be better attached to irregular or frequently deformed interfaces, such as the human tissues, joints of instruments, or soft robotics. In this field, conductive elastomer inks are a popular solution for the fabrication of flexible and stretchable electronic devices. The common method of making these inks is to mix elastomers with conductive fillers. The conductive elastomer inks have the advantages of being low cost and easy to manufacture, so they are very suitable for large-scale fabrication of flexible electronic devices through additive manufacturing, for example, the stencil and screen printing. The reason for conducting this research is the AC properties of these inks are largely unknown, and these properties are important for evaluating the application of these inks in high-frequency circuits for interconnects and the electronic devices and sensors. Here, the AC properties of three types of carbon-based composites PDMS, the carbon black 100% compressed, carbon black Super P, and graphite in the frequency range of 20 Hz to 1 MHz, and the equivalent circuit model used to fit these results are presented. This figure shows the setup of the AC analyzer. A 4-point measurement platform equipped with the front-end amplifier was used to measure the three types of carbon-based conductive elastomer samples. And the analyzer is used to obtain impedance and phase information. The AC analyzer results are shown here. The both plots of three types of carbon-based conductive elastomer, the carbon black 100% compressed, black Super P, and graphite. According to these plots, it can be observed that the difference in filler concentration can bring an obvious phase shift. At low frequencies, let me see here, the phase from approximately 0 means a more resistive behavior. Goes to positive means more inductive, and then falls to negative, which means more capacitive behavior. And this kind of pattern is common between all materials. Can be seen for carbon black Super P and graphite, the same. When the concentration of a conductive filler is low, the conductive elastomer will show obvious capacitance characteristic at low frequency. When the concentration of conductive filler is higher, or the conductive of the filler is better, the conductive elastomer can maintain the resistance characteristic in a wider frequency range. Based on the result curves, we analyze the structure of the elastomer and get the basic equivalent circuit. The filler particles in CB-PDMS can be considered as resistors. Multiple conductive fillers are connected to each other to form a structure like electrodes, and when two electrodes and the PDMS form a sandwich structure, this forms a capacitor, similar to here. Moreover, since the conductive passes at high frequencies often show inductance, this will also cause the elastomer to show inductive behavior. Therefore, conductive elastomer can be considered as an equivalent circuit formed by capacitors, resistors, and inductors in parallel, as shown in this figure. And on the right side, the good fitting result of carbon black Super B 17% can also prove that the equivalent circuit is basically in line with the prediction. So in summary, conductive filler concentration affects not only magnitude, but also phase in AC condition. Carbon black Super P and graphite fillers demonstrate superior AC performance to carbon black 100% compressed. Graphite achieves slightly better performance at high filler concentrations than carbon black Super P. The basic equivalent circuit based on AC results has been obtained and achieved a good fitting result. Thank you for your attention.